Welcome to ECGR 4101, 5101, and ELEC 4133. Welcome to the much bigger class, a much bigger classroom. Maybe I should say offhand, how many of you find it helpful to have recorded videos? At least you can check back on. All right, so I'll keep doing it. As I already have this class recorded once, as you well know, because lecture number 4, which you were supposed to watch last week, was available for you to look at. So, if you actually did watch last week, the problem is half solved for you. And in fact, how many of you actually went to go look at homework or notes number 5, or lecture number 5? I actually solved it in lecture number 5 from last year's class. So, let's solve it again. This is the answer to the exam. So, as I wrote on the screen, oh no, I wrote on this screen and now it doesn't show up there. Oh crud. Alright. It's a joke, guys. Alright. By the way, as I said, this is ECGR 4101, 5101, ELEC 4133, that's number 5. This is the solution. As we discussed last week, and was also in the video last week, if we want to read any one of these ports, what do we typically say? Oh, look at that. We have data, and to read the data, what do we say? All right, leaders. Port 1 dot. I will accept DR, I will accept port. Either one I'll accept, doesn't matter. DR dot byte. Ooh, but I really forgot something here, didn't I? We're going to cast it as an integer. And it will be port 1 dot DR data register dot byte. Once we do this, do you ever need to refer to port 1 ever again? No, because it's already stored. It's already stored as data in the variable called data. So now if we ever want to do a comparison with that, we're going to do a, what type of comparison? A bitwise AND. And what is the sign for a bitwise AND? The single AND. And so obviously we need to say if data is ANDed with, let's say we want to look at bit 0, right? What are we comparing it with? The value 1, correct? Because if our, let's say, just for grids, our data looks like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1. All right? What does this place indicate? What's being pressed? Pardon me? Switch 1. Switch 1. And what does that indicate is being pressed? And what is this? Oh, let's see, is it switched or not switched? Oh, it's not switched, sorry. And what does this indicate is being not pressed? 3, all right? So, that says if switch 1 is being pressed, correct? Oh, we're looking for not pressed. So what would be best to put in here? Just to make sure it's easily identifiable, we will go ahead and take that solution Then we'll say printf, and I said just put anything you want in there. So, based on this, what do you think the next one will be? If not, data bitwise 2. And then we'll have our printf. And for switch 3, and then we'll have our printf. So now what is the last thing we should check? The last thing we would want to check is if any of the 3 are not pressed. And so what would that be? Let's think about this. If a 0 in one place says it was pressed, right? Well, we want to find if any of them are pressed or if all of them are pressed. Which is it? Any of them are pressed. So if we AND it with 1, if we AND it with 1, 1, 1, if any of them have been pressed, will that work? So rather than me tell you the answer, I want you right now to spend a little bit of time, turn it to your neighbor, and figure, how many of you think you got this last line anyhow? Yeah, not too many, that's what I thought. So, right now, turn to your neighbor, spend a couple of minutes figuring out, now that you have a little hint from the ones above, figure out what could the answer be. So my ET friends here, and as you can see, it's a little bit different than your typical course because I have you stop and actually try and do some things as you go along. You guys use that often in other classes, or is it just kind of like spewing and take notes? All right. So welcome. Feel free to sit next to somebody of the same discipline or different disciplines. I do this once or twice during class, so that you actually learn as you go along, and then you apply it right away because you retain that. So, have fun. Has anybody solved it yet? Alright, you see somebody Who has a solution that uses as little code as possible? Diffuse character. Yes.
So data equal to 7.
Is it equal to 7?
Equal to 7.
Okay.
Data and 7 is equal to 7.
So if it's not equal to 7, that means that it will be something other than 7, right? One thing to do that we should have done earlier is mask it earlier. And so one easy way to have done that is to mask all the other bits to ensure that you didn't have anything else show up. All right? So the answer to this is and again, why would you not put a single equals sign? All right, a single equal sign is the assignment. And that would mean that you would set 7 equal to the variable data, and then of course you would have that true. Anyhow, notice that we don't have a not, right? Isn't C language fun? This is just like that close to assembly language. So, how many people are depressed after you see the solution? All right, good answer. I will still have. Don't forget, I give more than 15 quizzes for this class, so you'll have plenty of opportunity to drop your 3 lowest or 2 lowest assignments or 2 lowest quizzes. Yeah. All right, so I think for the sake of my own voice, I'm going to stay here rather than walk around like I usually do. You all can hear me pretty good, right? And of course, for those of you not from the South, you know y'all means you all, as opposed to all y'all, which means you all. So, as another example of masking, if you have to convert between upper and lower, you can use something like a and or an or you could subtract or do an and. So these are the situations here where you might want to do something else other than. Okay, no, I don't want to do that. So this might be a situation where you might want to do something else like an and. So if we have the value and we want to, if we have this variable right here, and let's say it's 0. All right, here goes nothing. Don't you know, just when I need it to work correctly, it doesn't work. Any hint? This thing is just like screwy. Here's one of the problems. I think I'm the first one to ever use this. So that works. Yeah, it's just doing this. This is the ultimate in annoying. I guess I'm going to ask the show. So, if I have the name 0 or the value 0, 1, 1, 0, 0, 0, 0, 1, 1, what is that in ASCII? What is that in ASCII? Not hexadecimal. In ASCII, it is the character lowercase c. So if I, by the way, I think in our parallel lines we have a single quote that indicates a single character, right? So if I want to, say, convert this into an uppercase letter, what do I need to do? I need to change that bit. Let's take a look up there. What's capital? So I want to get rid of this one right here. Right? So I want to convert to 0, 1, 0, 0, 0, 0, 1, 1. So how does one convert this one to 0? Can't you AND it with 0, oops, 1, 1, 0, 1, 1, 1, 1, 1, correct? And in fact, is that what I have up there? Yeah, DF, right? The other alternative is, I know that this is the value 32, so I can subtract just 32 from whatever that variable is, whatever you define it as. Now, will this always work? For lowercase letters, right? What about for characters? I mean, like strange characters. What about if it's already an uppercase letter?
Then we can add it.
You don't know, right? So you might have to put a lot of code in there to say, okay, if it's an uppercase letter, then subtract. If it's not an uppercase letter, then do this. Isn't it just easier just to say, do an AND, a bitwise AND? That way you can ensure that it's always done. And so that's some of the things I want you to think about is, when you're doing this code, just like, did you mean to use the single equal sign, or did you mean to use the double equal sign? You need to start looking at stuff like that when you're writing your code. Hey, is this colored? Oh, it's still the plain old white. How boring. Now let's get into arrays. We're still going through the notes that I have for this class for C programming. And in this case, we're going to talk a little bit about one-dimensional arrays as they are stored in memory. By the way, if I get too loud for you guys, you got to let me know because I can't hear very much back here. So for the specific identification, if you say at this point right here, man, I'm going to have to find out how this thing works because this is going to drive me nuts. Let's see if that works out. Nope. I think I need training. So I'll just go with this. So if we have the identification of, oh, a character array called buff1, which has a total of, wow, this is really loud now. What happened? Has 3 array elements. So what this will do is it will identify, remember character is 3 bits. I'm sorry, it's 8 bits. We have 3 of these, so it will take a total of these 3 locations. An integer we're identifying for our system is going to be 16 bits. So in this case, you're going to identify a total of 6 bytes to be able to, or that you're going to store in our array. In this case, we're just identifying an array. It'll have a certain size. The specific size is what you assign to it. In this case, ABC. We've already identified what's going to be in it. In this one, we identify a 3-element array of integers, and we give it a value. We could have just as well put the number 3 in here. Now, again, if we reference this specific location, let's say the C right here, it will be identified as what? I'm going to try something wild and see if this works. Oh, great. It gives me a keyboard that doesn't put anything anywhere, right? If I say, this is just absolutely worthless, isn't it? Your next screen press will be your right click. I don't like that. You know what they say insanity is? Doing the same thing again and again and expecting a different result. I think I have gone insane. As if somebody is telling me, here's the instructions I want to do. I'm going to read that while you're sitting here in class. I don't think so. Believe it or not, this does not even give me the option to change it. Rather than do this, I'm going to hit this button, which is a wonderful button, which will take me to my notes. Again, if we did a int buff3, obviously we're going to have the situation the same you can get from if buff. Does that look right? So in our array that is 8 bits wide, it will store 10, 20, 30, and these will be in 16-bit slots. Here's a good question. Did we cover in the last lecture, I can't remember, big endian versus little endian? Yeah, we're not going to worry about that right now. So later on, if we say int data, and data is equal to buff 2, what will be the contents of data? Because this is location 0, 1, 2. That's the important thing I wanted to remind you of. As opposed to other programming languages that start counting at 1, this one starts counting at 0. Wow, look what time it is. I'm just running out of time. Maybe I should stop giving quizzes. As another example, 2-dimensional arrays. Specifically, we're going to be looking at how you number the rows and columns. Again, in this case, we've identified the variable called buff2. And in buff2, you first look at each row, and then you look at each column, and that's how they are stored. Specifically, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. And then if you actually do any work with that, it'll store it in those specific locations. Do you really have to worry about that? Do you have to know how they're stored? Well, one thing you could use later when we talk about pointers, you might be able to use something depending on how far along it is in the array and just use a pointer instead of doing a specific reference like this. We're going to see an example of that later. In fact, here we go, pointers. One thing I need to point out of pointers, how many of you have used pointers before? Raise your hand high so I can get a good assessment. Ooh, a lot of you. All right. The ET guys back there, no? Oh, yes? Okay. The computer engineering guys up here, I think, are right. No. So, I'm going to get back behind the podium so you can hear better. This is a good slide to wrap your head around if you are having difficulty understanding pointers, because this tells you what the progression is at each step. So in this case, we are identifying two variables and we're identifying two pointers. As it turns out, variable I contains the number 4, variable j contains the number 3. P1 is a pointer. In particular, the ampersand here says, give me the address of variable I. Very often you may need to pass the address of something in a function. So this is how you get the address of it. Not the contents of that, but the address into it. Then P1 is going to contain an address. Specifically, it's 600, which, as it turns out to be, is the address of memory location I. And as a matter of fact, when you use the star P1, that basically says, take the contents of the pointer P1 and do something with it, as opposed to take the value of P1, or take the contents at P1, which is actually a pointer, a memory address. So that's why you see here, in this case, the address of variable I and the address of variable j are going to be stored into P1 and P2 respectively. That is why when we put the splat in front of these, everybody in the computer world know that, is this a splat? Yeah, it's a splat. And you know what the exclamation point is called? The exclamation point is called a bang. They've come up with these things in the past. The same way as, what is half of a byte? A nibble. Did you get it? A nibble, 2 nibbles make a bite? All right. Anyhow, that's because computer people have senses of humor, or so we think. At this point again, the splat P1 says, take the pointer P1, take the contents at that, or actually take the contents at P1, add it to the contents of P2, and store it in P1. P1 and P2 are pointers, and so we'll take the value 4 and 3, add it together, it'll store it to this memory location, because that's what the pointer is pointing to. And then, at this point, the contents of P1, it's an address, is going to be stored into the contents of P2. This slide is really critical to understanding all pointers. Again, if you have difficulty with this, just spend a little bit of time chewing on this. You never know when something like this will show up on a test or a quiz. Here's another example. In this case, we have an array of 18 elements. What's the What is the reference of the first one? A0. What is the reference of the last one? A17. We have a pointer. So it is going to say, give me the address of the fifth, or of A5, which is how many in? It's the sixth one in. And oh, by the way, what I want you to do is I want you to store 5 into that location, P. CP, as you see, P is a pointer, right? Then if you increment this, which one are you pointing at? You're now pointing at A6. Here's the interesting thing. Look at this. This is an integer pointer. So when you increment with the plus plus, you're not incrementing by the value of 1, you're adding the value of 2. That's because this is known as a pointer to an integer. So when this increment is done right here, it will add 2 to the value of P, And by the way, when you do this decrement, you're going back to A5. When you do the decrement, going back by 2 as well. This is another slide that you should understand how it operates with respect to pointers. And again, I'll say that it is assumed that you have a good grasp of C from a previous class. If you do not, you'll need to do a little bit more studying on notes 4, 5, and 6, because it assumes 4, 5, and 6 are just a recap. Now, the main reason you use pointers are specifically for data structures. Lists, trees, doubly linked lists, singly linked lists, queues, and other types of structures like that. And in fact, later on, we're going to take a look at those. Another reason you might want to use a pointer is when you make a function call, you don't really want to pass a whole bunch of values. What you want to do is you want to point the address to where those values are, because very often when you return from a function, you are not going to have more than one location or one value to be able to return. So if you need to change many variables, what you need to do is pass into the function the addresses of those variables that you want to change. So this is an example. By the way, if you are not familiar with some of the concepts of computer architecture, I put a link out there to a book by Patton Patel. There are some online notes that you could read to catch up on some of computer architecture. So I have a string, and the address to the beginning of this string is going to be called str. The address of the first element in the string is the exact same thing. And thereafter, string 1, string 2, etc. When you store any sort of information into the string, you are going to have a null character put at the end of it. So if we happen to have an array of 44 characters, whatever you assign to it, in this case testing, the compiler will automatically put the null character at the end of that. Why is that a good thing?
To identify the strings.
All right, to identify the string's end, because you may want to do some work with the string and go all the way to the end of the useful data in the string. So as an example, if we are doing some sort of string comparisons, it will do a print all the way up to the null character that it comes across. Oh, so some of these, oh no, that means I'm boring myself. I better move faster, right? So if you want to do some formatted output, printf, sprintf, and fprintf, are ones that you could use. sprintf prints to a string, fprintf prints to a file. The different syntax associated with this include things like whatever your characters are, and then any sort of arguments that you have after that. This is best showed with an example. All you need to keep in mind is that when you're looking at a particular format, you identify things like %d saying displayed as a decimal, or displayed as a floating point number, or displayed as a hexadecimal number, or displayed as a character, or displayed as a null terminated string. So let's look at some good examples. If you identify two 30-character arrays, S1 and S2, and in this case we've identified three integers that have the values of 5, 10, and -30. And in this case we identified the character CH as holding the single value, which is $. $sign would be what ASCII representation, what hex representation of that ASCII character. Here we go. So $sign will be the value 2, 4 in hex. Going back to where we were. What we're going to do is we're going to put into the string S1 the value testing. And so in testing, you will see, or in S1, you will see testing with the null character all the way at the end. If then in S2 we say, give me the value character A, character equal to, and then a decimal number. In this case, the decimal number of variable A is 5. The decimal number of variable B is 10. And that's what we will get over here. And this will be the specific string with a null character at the end associated with it. Notice that here's an opening quote, there's a closing quote, there is a blank space right here, and that will be inserted in that string as well. Again, over here, we're going to put B is equal to, and in this case, we're giving it a hexadecimal value. 10 in decimal, remember, is A in hexadecimal. We're putting a decimal here. And in this case, then we're saying, oh, if we want to specifically say, print the value or the characters B = 0, X, and then whatever the value is, yeah, that'll turn out to be better. Now, in this case, we're going to say, take whatever is in string 1, which in this case is, what was set up here, B is equal to 0XA. It will append whatever is in string 1 to string 2, and there you go. All the way at the end is going to be the null character. And again, here we're going to put the information %C, which says what? It's going to be the specific character, and it will be, in this case, a $sign, then there's a space, then there's another character, in this case S1 or S2, will only give you the very first character of the string, which is S. There are other variations. You could actually format how you want your floating point to look. I think I'll leave this. I see too many people yawning, so I'll leave this to your own examination. Yeah, I see you yawning out there. I'm not going to point out who in particular I saw. And again, these are more examples. I don't really need to go into this in much detail. This is a recap for many of you. If this is new for you, you can just take a look at these slides and get a better idea. There are certain string operations that you can use in C. In our embedded board, you can still use these, and you can actually display them on our display, our LCD display. display. In this case, Limburger cheese. Anybody like Limburger cheese? I think it's a very much maligned cheese. So in this case, we're going to copy string 2 into string 1. In this case, string 1 will now hold the word Limburger with a null character all the way at the end. And in this case, we will have and concatenate the word cheese to blank puffs, and you will have cheese puffs in that array. Or if you're a fan of South Park, cheesy poofs. For those of you who don't know South Park, that will be a wonderful education for you to take in your own time, right? Because otherwise, okay, I have to make the question. How many of you have watched South Park before? All right. So let's see, can I do my best Cartman
please
accent? Yes. I can't do it, I'm sorry. I like cheesy puffs. I can do Muppets characters so much better. In this case, there are other uses of string concatenation where you can say cheese puff and you only want to pull the first 4 characters over. And then you could also do other examples. For example, string comparison. We'll say where do these two actually, when you're comparing them to, what will you be able to compare, and where is the first location where they're different? And in this case, if you do a comparison of cheese with cheese, it'll say that they're precise and it's 0. For those of you who are Lord of the Rings fans, you'll know who Smeagol and Deagle are. Again, another example, give me a comparison, or return the pointer to the first occurrence of the letter G in this string, and in this case it's 0, 1, 2, 3, 4. It'll give you the pointer to the 5th position, or S1, 4. In this case, it will also do the return the last character, and this one it'll concatenate it together. So now let's shift gears and go into another concept, dynamic memory. Now, very often when you're working with a system, you don't have specific variables that say, oh, I want this variable to be, oh, let's say 4K big. Because in most computer applications, the amount of memory you need really depends on specifically what you're doing. To give you an example, let's say you are recording voice on an answering machine. Is that my example on the next page? Now it is coming up. So I'll address that in a minute. So let's say you're recording the voice in an answering machine. You don't know how long somebody is going to talk. So what do you do? Well, you allocate space for the biggest possibility, and then when you need to save that off somewhere, what you'll do is you will only grab as much space as you need to save something off. And that is a dynamic memory allocation, or what we often call as malloc, memory allocation. What you do is you say, give me the address to the beginning of this many bytes of memory, and that's what a malloc will give you. You also need to identify how big that memory is going to be with respect to, is it going to be a character? Is it going to be an integer? Is it going to be a float? You can actually identify how much it's going to be. So if you do a malloc of 200 characters, how many bytes is that? 200 bytes. If you do a malloc of 200 integers, how many bytes is that? 400. And so the malloc will allow you to allocate the specific size of each individual element in that and a certain number of those elements. So in this case, it also will give you back a address, and you'll use it in this situation. So in the malloc, I should say, also will give you the specific size of a single element, and then calloc will do a whole bunch of it. So in the case of calloc, let's say you have a certain number of elements, 200, size of integer. So the function called size of integer will return in our system how many, what size? 2 or 4?
2 bytes.
All right, 2 bytes, so it'll come back with 2. Unless somebody thinks it actually does 4 and can back it up with something in our documentation. I believe it is 2 in our board. So if I'm wrong, please let me know. That's for a free trip to the prize closet, right? So in this case, we will identify a single element, and J is a pointer. So at this point, it'll just point to a single memory location. But in this case, whoa, we get to allocate a whole bunch of things. So if num elements is the value of 100, right? Or 200, as I said in my example earlier, then we have 200 locations to store all the integers we might use. Keep in mind that calloc and malloc return a pointer. So it returns an address where this specific space will be used by you. And if there isn't enough space, then it'll come back and it'll tell you so. Now the interesting thing about a malloc and a calloc is that there are operating system functionalities that will actually allocate memory for you. So this is something, calloc and malloc is something that is a C instruction, but there needs to be some sort of operating system behind that which will allow you to dynamically allocate memory and then free it up. Because it would be really bad if you kept on saying, give me more memory, give me more memory, give me more memory, and never freeing it up when you're all done, right? So you have to free it up when you're all done. So let's take a neat little example. I think this will probably take us to the end of class. That's 10 minutes from now. Don't pack up yet. So the example that I have here is a simple voice recorder. While you're pressing the switch, you will sample the microphone and store it in some temporary memory location. Now this could be they have these little handheld things, right? Note to self, pick up eggs from the grocery store. And so here I'm going to use my record switch to record it, and then later on I'm going to play back or maybe even delete it. So, all right, here we go. Note to self. I am going to get groceries. There we go. So I recorded something. Now that I've recorded it, I want to save it. So what I'll do is I'll allocate some space with a malloc. When I do a malloc, it gives me an address. So I'll need to copy all the data over from that location. Then I'll need to build a data structure that has 2 things. Number 1, it points to the top of that saved recorded message. Because remember, this one up here is just temporary. So I'm going to save it over here. This memory location here will point to the top of this. And usually in that as well, it'll tell you how many bytes that is. And then I'll also need to point to this specific record from another variable. And usually at this point we also, let me go up here, we also identify this as a null right here. There's nothing in here. So now I'm going to record something else. Let's see, I'm going to record something, I think this goes a little bit longer. So I'm going to record, and then make sure to pick up my son. That's it, that's all I had. So now I have this temporary space. I'm going to malloc, and I'm going to get some space somewhere else. Then one by one, I'm going to copy all the bytes of that data over. And then I'm going to create another bit of memory for my data structure. Since I want to kind of like keep a string of all these things I've recorded, here's my first one, here's my second one, I'll point to what I've recorded here, and then I'll use this part of the data structure here to say, okay, and here's the next recording. And then maybe one more time I'll record something, and I'll say, make sure to go to the flying saucer to get a beer. There we go. And now I've recorded that. I will allocate space with the malloc. I will copy everything over from my buffer. Then I will create another part of the data structure. That can be done with the malloc, allocating only a little amount of space. I'll point to what I've recorded, and then I'll be able to say, all right, here is a list of my recordings. I'll go to the first one. Is that the one I want? No. Try the second one. Is that the one I want? No. Go to the third one. Is that the one I want? No. Go over here, and at this location it says there's no more recordings. So now I'm going to go through and I'm going to play and maybe record something, and or maybe delete something. And so I'll say, okay, I want to delete number 2. So to do that, I will free up that space. And by freeing it up, I give it back to the operating system, and the operating system will be able to identify that as usable by somebody else. And by the way, doing the freeing associates that I will get rid of any pointer to that in this data structure right here. And oh, by the way, since I got rid of all examples of that, or all cases of that, I need to make sure that I point between this recording and the next one it's going to see is this one over here. And that is done using a data structure, a linked list of recordings. Now this is where I am not sure who in this class has had this background. So who has had a data structures course? Raise your hand high. Ooh, this is not good. How about at the graduate level? How many of you had it? No data structures at all? All right. So queues and linked lists and other fun stuff like that? Ooh, this is like new stuff for all of you then. All right, so I'll give you a taste of what we're going to talk about. I am going to ask the following. For the for next class, which is on Monday, read through these notes that I've provided for you in PDF form out in the course website, because I will ask a couple of simple questions about these notes, specifically about ones that follow after number 36. All right? So before I go any further, I would like you all to, as a part of this class, read that, because you'll never know if you will show up on Monday and a quiz will be ready for you based on the reading of the notes. That's it. Mr. Recorder, if you could turn it off. Thank you very much.